Okay, hello, welcome to the site visit. So we'll now hear a presentation by Matthias Gaberdiel, who is going to tell us about his recent work in the context of the string theory subproject of the Swiss map NCCR.
Thank you, Marcus. So let me share. So what I'm going to talk about is recent work that I've been doing mainly with Roger Kopaguma and my former PhD student Lawrence Eberhardt about trying to prove the ADS-CFT correspondence. So let me start by trying to remind you about what the ADS-CFT correspondence is, at least in its simplest incarnation. So the simplest incarnation is string theory and ADS5 cross S5 is believed to be dual to the n equals to 4, so very supersymmetric SUN gauge theory in 4 dimensions. And that's a theme that's been dominating research in string theory for the last 20 or so years. It's a very interesting duality because it relates two theories to one another in regimes that are in some ways complementary. So if you look at the strongly coupled regime of the gauge theory, that corresponds to something you can you have under very good control on the string theory side. You can apply the supergravity approximation. Whereas if you're looking at the regime where perturbative methods are good for the gauge theory, so where the coupling constant is small, that corresponds to something that's typically relatively inaccessible from the string theory perspective. So it relates one side of the theory, of one theory to that's solvable to the other side on the other theory that's typically hard to solve. And as a consequence, while there's very good evidence for it, it's very hard to prove the ADS-CFT correspondence because typically you only have one of the two sides under control, whereas the other side is difficult to describe and get under control. So in order to make progress with this, we've decided to look at the regime where it's where we have the gauge theory under good control, which means that we have to get control of the tensionless limit of string theory. Tensionless limit means that the string size is the string is very floppy. It's as large as the size of the space in which it propagates. And in order to simplify the problem further, we've decided to also go down in dimension and look at the low dimensional version of this duality, namely string theory in ADS3 cross S3 cross T4. So instead of ADS5, you look at 3-dimensional ADS string theory, for which the dual is believed to be what you may think of as being the analog of super Yang-Mills in 2 dimensions, which is the symmetric orbifold of T4. And the symmetric orbifold theory itself is believed to be the analog of free super Yang-Mills theory. So what we've managed to identify over the last few years is the specific string theory that we believe or claim to be dual to this concrete 2-dimensional conformal field theory. That's a certain string background. It's in this tensionless regime. It involves, has a solvable worldsheet description in terms of a supergroup Resumino-Witten model based on a super Lie algebra PSU 1,1/2. And what we claim is that we have an understanding of the string theory that's dual to the specific conformal field theory on the other side. So this is a regime where both sides of the correspondence are simultaneously under control. So both sides are explicitly solvable. They have both free field realizations. And in particular, that has allowed us to show that the spectrum of the two descriptions agree exactly in the large n limit, and not just for BPS protected quantities, but for the full spectrum of the theory. And furthermore, to show that the correlation functions of the two descriptions also match up, i.e. that the correlation function that you can calculate in this 2D CFT, i.e. the analog of free super Yang-Mills, can be reproduced in a highly non-trivial way from the worldsheet description of this string theory in ADS3 cross S3 cross T4. So the theme of this most recent development is that we've understood that the worldsheet plays the role of the covering surface of the symmetric orbifold. In order to calculate the correlators of the symmetric orbifold, a covering surface naturally appears. And what our analysis has given very strong evidence for is that the worldsheet actually plays the role of this covering surface. And this not only shows that these correlation functions match, but it also in some sense shows that they manifestly match and that they will also match to all orders in 1/n, not just in the large n limit. So the large n limit is in some sense the classical string theory, and 1/n corrections involved, and also the higher genus corrections on the string theory side. Now, future directions, or what we are currently working on, is to directly make use of this free field realization. The theory we get looks very much like a topological string theory, so we want to understand this from first principles. And there are hints that it has to do with twistor string theory, and that's also something we are currently exploring. And that's what I'm working on with my PhD student Andrea Day and Bob Knighton, as well as with Rajesh Gopakumar.
Matthias, thanks a lot. I have a small question. So this idea, which is displayed on this slide, that the worldsheet plays a role of a covering surface, is it specific to this lower dimensional version of ADS-CFT correspondence, or you expect something similar for the higher dimensional versions as well?
That's a good question. I think on the face of it, it seems to be specific to this low dimensional setting, although similar features may also play a role in higher dimensions. How this generalizes to higher dimensions, I think, is an interesting, certainly very open problem. What our intuition is that these free field realizations that we found, they have a very natural generalizations for what you could believe should describe ADS5 cross S5. And what we believe is that, for example, the topological nature and the relation to twistor string theory will also generalize to the case of ADS5 cross S5. And that there one will be able to relate this to free super Young Mills. Whether the covering surface will directly come into this, that I'm less sure. But the covering surface is quite specific to the symmetric orbifold. So I'm not entirely sure that would be visible in free super Young Mills.
Perhaps another question. Could you briefly indicate what kind of mass are you using in this research?
So the mathematics is very much representation theory of super Lie algebras or Wessel-Minowitten models, affine Kac-Moody algebras. So the thing that makes the worldsheet theory tick is a affine Kac-Moody algebra based on the super Lie algebra PSU 1,1/2. And it sits at a very specific level. And at this level, it is it behaves like SU2 level 1. So it has lots of additional structure, lots of null vectors. So it's the representation theory that controls this theory. And we've managed to harvest insights from this representation theory to understand, for example, the structure of the correlation functions on the worldsheet. These are highly constrained by this symmetry and thereby reproduce the structure that you would expect from a covering surface. The structure from a covering surface is such that covering surfaces typically don't exist. So these correlation functions of this worldsheet theory have the property that they are mostly zero. They are zero unless the parameters that go into the definition of the vertex operator satisfy some magical identities, some holomorphic type identities. And we've used the representation theory of PSU 1,1/2 to show that the ward identities on the worldsheet are such that they seem to demand a localization property of that kind.
May I ask you another question?
Sure.
This covering structure reminds me a little bit of what happens in the string description of 2D Young Mills, right?
Yes.
So it's like, these are Hurwitz coverings. So is there some mathematical parallelism here?
Possibly, yeah. So how this relates to 2D Young Mills, I don't know. That I really don't know. This is, but it surely is very, yeah. So it's Hurwitz theory. So it's the Hurwitz numbers. It's a very simple structure. It's, but here it comes out of really solving the ward identities coming from this complicated super Lie algebra. This is so at the moment we are really, in some sense, in the early stages of really unraveling all that's going behind the scenes. We've managed to, with some quite technical effort, to identify ward identities that constrain the correlators very strongly. And using that, we've managed to show that they really reproduce the structure you expect. But at the moment, it's some quite complicated analysis. And there's sure enough going to be a more conceptual way of understanding this, which we haven't yet managed to unravel.